Example 4.24. A uniform magnetic field of 3000 Gauss is established along the positive Z direction. A rectangular loop of sides 10 centimeter and 5 centimeter carries a current of 12 ampere. What is the torque on the loop in the different cases shown in figure? What is the force on each case? Which case correspond to stable equilibrium? Now see, in each case, here the direction of the current that is given to you. You want to calculate the torque on the loop in different cases. Now see, suppose here first we think about the data given to you. Magnetic field that is 3000 Gauss, so that is 3000 into 10 raised to minus 4 Tesla. So we can write that is 0.3 Tesla and it is in Z direction. Keep that thing in your mind. Now area of the loop that is 10 into 5, that is 50 centimeter square. So into 10 raised to minus 4. So that is 50 into 10 raised to minus 4 meter square. Current passed through the coil that is 12 ampere. Now, if you want to calculate torque, then torque that is mb sine theta. M that is magnetic moment. So we have to calculate magnetic moment also. Magnetic moment that is I into A. So I that is 12, area that is 50 into 10 raised to minus 4. So magnetic moment that will come to 6 into 10 raised to minus 2 ampere meter square. Now, suppose we think about this first case in which the loop that is given to you as shown in the figure, that is in YZ plane, and the current in the loop that is anti-clockwise direction. Now see here, how to find out the direction of magnetic moment. So we discussed in the theory. Magnetic moment M that is I into A. So we have to use the right hand thumb rule. Place the finger in the direction of the current. So thumb will be giving you the direction of the magnetic moment. So in this particular case, if we place the fingers like this in anti-clockwise direction, then thumb that is outward means the direction of M that is perpendicular to the plane outward, so that is in X direction. Okay, so torque tau that is mb sine theta or m cross b, and you will get the torque that is 1.8 into 10 raised to minus 2 Newton meter, and that will be in negative Y direction. Net force on the coil. So net force on the coil that will be 0, because say if we think about this particular side and this side. So for these two, the B that is parallel to the current and anti-parallel to the current. So force F that is BIL sine theta as per that 0. Then for this upper side and this lower side, force will act on both the sides, but currents in both the sides are mutually opposite. So magnitude wise, the force will be same one, but the direction will be opposite. And therefore, net force that will be equal to 0. Clear up to this one? Now see, this B case. In that also the current that is in anti-clockwise direction, your loop that is in YZ plane. So the answer that will be same as we obtained in the first case. Clear to all of you? Now see, in case of C, if we think about the dipole moment, then fingers in the direction of the current, thumb will point the direction that is negative Y direction. Okay. So M that is minus 0.06 J caret, B that is 0.3 K caret, tau that is M cross B. So that is minus 1.8 into 10 raised to minus 2 I caret Newton meter. Means torque that is in the negative X direction. Now net force that will be here 0, but coil is not in equilibrium. Why not in equilibrium? Because torque is acting, it implies that there is a couple of force. Two forces will be such that which will be equal in magnitude, opposite in direction, but not collinear. So vector summation of the forces that will come to 0. So net force that will be 0, but coil will not be in equilibrium because couple will produce the torque, and due to torque it will be rotated. Clear to all of you? Now see, in D case, here the angle of the coil with respect to y-axis that is given to you, but your coil that is parallel to the z-axis. When your coil is parallel to the z-axis means magnetic moment that is perpendicular to the coil, therefore it is perpendicular to magnetic field also. So when magnetic moment is perpendicular to z-axis means it is perpendicular to B, your torque that is mb sine theta. Value of mb that is 1.8 into 10 raised to minus 2 sine theta, that is sine pi by 2, that is your torque. Okay. And now if you think about the direction, then that will be at an angle 240 with positive x direction, because with respect to positive direction, you have to take the angle in anti-clockwise direction always. And net force again 0. And when torque is acting, it implies that coil will be rotated. So it is not in equilibrium. Then E. So see here, coil is in XY plane. So when coil itself is in XY plane, it implies that the magnetic moment that will be along Z axis. Okay. So if B and magnetic moment both are in the same direction, then theta is 0, sine 0, 0, torque will be 0. Clear? And here, if we think about the net force, then net force that will be 0, torque is not acting here. So your coil that is steady one, it implies that we can say it is in equilibrium state. Then in F case, again the coil that is in XY plane, but the direction of current that is opposite than in the case E. So magnetic moment that will be in negative Z direction. After all, when it is along the Z direction, the torque that will be equal to 0. Here you have to take K cross K with negative sign. Rectify that. A dot અહીંયા ભૂલથી print થઈ ગયું છે. Clear to all of you? 4.25. A circular coil of 20 turns at radius 10 centimeter is placed in a uniform magnetic field of 0.1 Tesla normal to the plane of the coil. If the current in the coil is 5 ampere, what is the total torque on the coil? B. Total force on the coil. C. Average force on each electron in the coil due to the magnetic field. The coil is made of copper wire of cross-sectional area 10 raised to minus 5 meter square, and the free electron density in the copper is given to be about 10 raised to 29 per meter cube. Now see, total number of turns given to you in the coil, that is 20, radius of the coil, that is 10 centimeter. So that is 0.1 meter. B, that is 0.1 Tesla. Current through the coil, that is 5 ampere. Now see here. It is placed in the uniform magnetic field normal to the plane of the coil. Field is normal to the plane of the coil. So this is the plane of the coil and normal to it. So field is like this. So if we take the area vector for the coil, which is also perpendicular to the plane of the coil, means A means area vector and B, the magnetic field, both will be in the same direction. And therefore, theta, that is equal to 0. Now, first we want to calculate the torque. So torque tau, that is NIAB sine theta sine 0, 0. So torque is 0. Now, total force, that is also 0, because if we consider any current element on the circumference of the coil, then exactly for the diametrically opposite current element, the direction of the force that will be opposite than the first one. And these two forces will be equal in magnitude, opposite in direction, so will cancel each other. So in this way, the net force that will come to 0. Now, we want to calculate average force on each electron, because when the current is flowing, means that is constituted due to flow of electrons. Electrons are charged particle, and when any charged particle is moving in the magnetic field, the force acts on it. Now, in chapter number 3, we discussed J, that is NEV. And J, that is the current density, that is I upon A. Now, force on the electron when it is moving in the magnetic field B with velocity V. Now here, the velocity and magnetic field both are perpendicular to each other. Therefore, simply we can write magnitude-wise the force, that is EVB. Substitute the value of V from this one. So that is I upon NEA, or simply you can say substitute the value of EV directly. So that is I upon NA. Now B is given to you 0.1. Current I, that is given to you 5. Total number of, number density of electrons, or we can say number of electrons per unit volume, that is 10 raised to 29. And area, that is given to you here by pi r square. So substitute the values and you will get answer. Sorry, area is given to you here 10 raised to minus 5 directly. So substitute its value and you will get the answer. 4.26. A solenoid 60 centimeter long, end of radius 4 centimeter, has 3 layers of windings of 300 tons each. A 2 centimeter long wire of mass 2.5 gram lies inside the solenoid near its center, normal to its axis. Both the wire and the axis of the solenoid are in the horizontal plane. The wire is connected through 2 leads parallel to the axis of the solenoid to an external battery, which supplies a current 6 ampere in the wire. What value of current in the windings of the solenoid can support the weight of the wire? Take G, that is 9.8 meter per second square. Now suppose this is the solenoid. See, like this. This is the axis of the solenoid. Okay. Now on the axis, a small piece of wire is placed here, just like this one. This is a piece of wire and it is placed here. Clear to all of you? This is the piece of wire inside the solenoid on the axis of it. And this one is perpendicular to the axis. Now, these 2 ends of the wire are connected with the battery. Battery is outside the solenoid. Then current flows through this one. Current is also flowing through the solenoid. It implies that along the axis of the solenoid, there is the magnetic field. So this particular current carrying wire is in the magnetic field of the solenoid. So on this wire, the force ILB sin theta, but this wire is perpendicular to the axis and field is along the axis, means theta is 90. So force on this wire, that is ILB. Now, if this particular force that is exactly equal to mg, then here the wire that will be balanced, or we can say it will remain suspended inside the solenoid. Now, for that, how much current should be passed through the solenoid, that is asked here. Now, question clear? Now see, length of the solenoid, that is 60 centimeter, so 0.6 meter. Radius of the solenoid given to you, but it is not important. Now, what should be the current through the solenoid that we want to calculate? 3 layers of winding, each with 300 turns in the solenoid are there. Okay. Now, length of the wire, that is 2 centimeter. So that is 2 into 10 raised to minus 2 meter. Mass of the wire, that is 2.5 gram. So that is 2.5 into 10 raised to minus 3 kilogram. Current through the wire, that is 6 ampere. And G that we have to take 9.8 meter per second square. Now see, inside the solenoid, the magnetic field produced, that is mu 0 n I. Mu 0, that is 4 pi into 10 raised to minus 7. And that is number of turns per unit length. Here see, total number of turns, that is 3 into 300. 3 layers are there, and in each layer 300 turns are there. So total number of turns, that is 3 into 300 divided by total length of the solenoid. So that will give you number of turns per unit length. Current passed through the solenoid, that we have to find. Okay, so keep I as it is. So here your answer, that will be 6 pi into 10 raised to minus 4 I. That is your B. Now, in this particular magnetic field, the current carrying wire is placed. So, to balance the weight of the wire, the magnetic force on the wire, which is I dash BL, that should be equal to mg, where I dash, that is the current through that wire. So F, that is I dash LB, I dash, that is 6 ampere, length of the wire, that is 2 into 10 raised to minus 2, B that we calculated previously, that is 6 pi into 10 raised to minus 4 into I, that should be equal to mg, where m, that is 2.5 into 10 raised to minus 3, take G, that is 9.8, and now solve this equation and make I as a subject of equation. You will get the current through the solenoid. Clear to all of you? 4.27. A galvanometer coil has a resistance of 12 ohm. And the meter shows full-scale deflection for a current of 3 milliampere. How will you convert the meter into a voltmeter of range 0 to 18 volt? So here, full-scale deflection is obtained by 3 milliampere, means current capacity that is given to you, resistance of galvanometer is given to you, and you want to measure maximum 18 volt with the help of voltmeter. So resistance of galvanometer 12 ohm, current capacity Ig 3 milliampere, that is 3 into 10 raised to minus 3 ampere, and voltage, that is 18 volt. Now to convert galvanometer into voltmeter, we have to connect large series resistance with the galvanometer, and its value, that is R equal to V upon Ig minus Rg. So V, that is 18 volt, Ig, that is 3 into 10 raised to minus 3, and Rg, that is 12. Solve this one. You will get the value of the series resistance. Okay. So this much resistance that we have to connect in series with the galvanometer, and then after, by applying known potential differences, we have to recalibrate its scale. Then we can say now it is converted into voltmeter of range 0 to 18 volt. Clear to all of you, beta? Point 28. A galvanometer coil has a resistance of 15 ohm and the meter shows full scale deflection for a current of 4 milliampere. How will you convert the meter into an ammeter of range 0 to 6 ampere? See, again in this example, the resistance of the galvanometer given to you, Rg, that is 15 ohm. Its current capacity, Ig, that is 4 milliampere. So that is 4 into 10 raised to minus 3 ampere. And we want to convert it into ammeter, which can measure 6 ampere. So I, that is 6 ampere. Now to convert the galvanometer into ammeter, we have to connect a small resistance parallel to the galvanometer, which is known as the shunt. So the required shunt, that is, as per equation, Rs equal to Ig into Rg upon I minus Ig. Ig, that is 4 milliampere, so that is 4 into 10 raised to minus 3. Rg, that is 15. I, that is 6. And Ig, that is 4 into 10 raised to minus 3. Solve this one, you will get the value of shunt. Clear to all of you?